upload the presentation and the video on YouTube, like right, John?
Yeah, sure. So the videos will be uploaded to the aighana YouTube channel, and the link will be made available as soon as the videos are ready. So
So
yeah.
yeah, I put in the presentation a link for my LinkedIn account. We can of course we can contact on there.
Sure. Sure. Yeah, that is your code available on the public GitHub repo?
Yeah, I uploaded it. So I sent it to John. I think he will also upload it alongside with the slides and video.
Yeah, so the link is available to the code. Everything is there, so we'll be making it available. So yeah, I think there are no further questions. We would continue as they come. So I want you to go back to the input data, the shape of, I mean, the diagram where you talk about the processes, or
This one.
I mean, just take us through your yeah, yes.
So
How did you handle the data to put it in your neural network?
so
Like break it down.
yeah.
It's
We
much
have
simpler.
so in the data set we have like as I mentioned before 13 very large satellite images, like 4,000 6,000 pixels. Sorry, which are not feasible to work on with the neural network or any other model. So again, so I tried only to take the relevant information for each field. So let me get back to this image. So simply for like this box, I calculate the center pixel of it, and then I try to then I take like a 32 by 32 rectangle around this center to enclose all the pixels of the field inside this 32 by 32 batch, and any to also to like have to include all the other information. I take the 32 by 32 batch for all the spectral bands and all the time steps. So each crop field is represented by a 4D matrix with the number of time steps, by the number of spectral bands, by height and width. The second part in the data generation is like the input field mask. So we have like a lot of fields with very little, very small number of pixels. So I wanted to know to differentiate between the size of each field by having a mask that includes how many pixels are there for each crop field. And this mask was used afterwards in the pooling layer to only take the relevant information into consideration.
So we have a question. Someone asks you, Varun Prop Hacker says that why did you choose 32 by 32?
So that's a good question. So I started by 8 by 8, increases to 16 by 16, 32 by 32, and 32 by 32 will give me the best results. And after like tried to increase it more, it didn't give me good results. The model were slow, and the surrounding information was too much and unuseful to the model. So it's just by experiment.
Oh, okay. So it was through experiment that you went with the 32 by 32.
Yes, yes, yes.
Yeah. So if I understand you well, so this 32 by 32 is able to like cover for if the crop field is large, at least the 32 by 32 is able to cover the major part of it. I mean, so it will cover, take most of the information from the crop field. And if it is small, like as you mentioned, that sometimes it's 4 pixels only. So this 32 by 32 will cover everything, including some fields around it. Is that right? So that
Yes.
you are sure that you don't lose much information.
Exactly. And it's so I saw some approaches in the competition that tries to like learn on the only the pixels of each field. But I think on this approach worked better because I gave the model like more surrounding information about the crop field, which seems to help very much in the performance. So I take into
Okay.
consideration if I have like 4 pixels, I take like the surrounding pixels can also help identify the planted crop in this area.
Okay. Is there a way you would want to talk about your network architecture? I think.
Sorry.
Yeah. Yeah. So here, for instance, the input field, we have one by one by each by the, like, could you hit on that
Yeah,
again since we still have some time left?
yeah. So the goal of the masked average Boolean layer is to summarize the features for each time step. So in order to have like instead of a 3D matrix for each time step, to have like 1D vector only on the feature vector for each time step. So the way I summarized the feature was to uh, multiply the mask by the input feature for each spectral band and for each time step, and take the average across the valid pixels in the mask. So suppose we have like 4 pixels that are on in the mask, and the rest are zeros. So in the denominator, I will have, and this summation will be equal to 4. And in the numerator, I will have only the features of 4 pixels that actually taken into consideration and being summed in this equation.
Okay, that's right. So back to the previous slide, the architecture again. Yeah. So
Yeah.
the first one, I mean the input field masks. So we have one by one by H by W.
Yes.
Uh,
And the
yeah.
other input was T by 128 and HYW. So it's I just repeated. So the mask is universal to the spectral bands and the time step. So I just repeated it multiple times in order to apply it on all time steps and all the 128 features.
Okay. So for the first input, for instance, like one by one by H by W. So the H and W would be your 32 by 32 in this case. H
Yes.
32 W 32. Now, what about the spectral bands, the RGB and the other ones?
Yeah, so for this one is included in the input patches. So the input patch which has the information of the spectral bands and all the time steps has like the number of time steps by 15, which is the number of input spectral bands by height and width, which is 32 by 32. So I included it in characters the time and HLW to as I like I did multiple experiments with different sizes and time steps. So
Okay.
whatever the time steps and height and width, the same network architecture should work the same way. So
Okay.
the convolutional neural network tries to extract new features from the 15 spectral bands, which in my case extracted 128 new features using a series of complex operations.
All right. That's cool. Okay. So we have a question here that what are the three vegetation indices you used?
You mean the vegetation indices?
Yes, the added ones, the three you added.
Yeah. Yeah. So I added the normalized difference vegetation index, the NDVI. I added also the normalized difference water index NWI. So the NDVI is a combination of the red channel and infrared channel. And the NDWI is the combination of green and infrared channel also. And I added like a third index. I don't know actually its name. I tried to search if it is available in the research papers. But it's just like the blue channel combined with the infrared. The three indices helped a lot in the training.
Okay. Does that answer your question? Okay. All right. So we also have another question. Can you explain a little more detail on how 15 features got to 128? Can you give an example of some of these new features?
Um,
15 features. I think that would be the channels. I mean the yeah.
yeah, so the I use like three layers of convolution. So in the convolution, you have like a kernel that you pass across all the pixels you have, and the kernel has like an input features and output features, just a matrix. So in our case, we have like an input of 15 features, and the output is 128 features. And after you apply the convolution, you have like a nonlinear activation layer, like rectified linear unit, for example. So it's pretty standard in deep learning to use for like generating features for in a complex space or high dimension space.
Okay. So well, if that answers the question, I think that's okay. Or maybe the person will ask again if it's not clear. But we have another question that says, why did you remove the band 11? I think the B11 that you took off.
Yeah. So
Why?
we have 13 spectral bands, as I said before, originally. I wanted, I made like a test to see if all the features actually contribute to the model performance. I made like an experiment in which I tried to remove only one of the 13 and train the model and see the performance. When I removed the band 11, which is one of the shortwave infrared bands, the performance actually increased. So just I removed it. But any other band, removing any other band hurt the performance. It's like a feature selection step to see the importance of each feature.
We have a question that for small or large shows. I think I missed some of the questions. Yes,
Uh, yeah,
on your some of the questions at my end.
yeah. So I didn't scale them. I just take the 32 by 32 around the center. So no scaling was applied. I wanted to keep the information in its original form, and and like to differentiate between the sizes of each field. I use the masked average masked pooling layer to take into the account how many pixels each field has.
Okay. Now, going back to the field, I mean the image. Could you go back to that image, the image of the field?
This one.
No, no, I mean yeah, here, yeah. So you mentioned that there are about 13 classes.
7 classes.
7 classes. And,
Yeah, yeah.
and yeah, so I was guessing that these colors could be the possible classes. So each color would be a class.
Yeah, yeah, yeah. So this image, I forgot to mention that I just I'm showing it. It's originally drawn in one of the Radiant Earth Foundation posts. So
Okay.
just I made the reference. So I tried to search about their class coding. I didn't actually find it, but my guess is like the blue is definitely the maze because it's all over the place, and this is
Okay.
our dominant class.
Okay. Apart from the maze, are there other classes? I mean, could you mention the other classes?
Yeah, yeah. So
Just
it's cassava, common bean, and other 4 classes that are intercropping actually, which made
oh,
things much more difficult. It's
okay,
maize and common bean, maize and cassava, maize soybean, cassava and common bean. Uh, yeah,
okay.
I tried to make use of this information, but it didn't work. It didn't work at all.
So that do you think if you had used object-based analysis instead of the pixel-based analysis, the accuracy would have performed better, or the accuracy would have been better?
So the data come in the pixel format. So if so, the information sorry. So these drawn rectangles or shapes are exist in both training and testing. But if we are going to make a system that should not only classify the area but also find it and find its boundary, and then we should think about whether we need to use the object-based learning or pixel-based segmentation. But in my case, this was already done. I didn't quite have to do it to do anything to change it. So in this, and so the objective was only to do the classification.
Okay. So if I may ask, how heavy is the data and how did you handle that? Because going through your code, I saw a comment somewhere. He said that do not run this in your local machine or something like that.
So this was like so part of the code was to do the mix up augmentation. So I had to uh, load all the data at once in the RAM, which is not like the most optimized thing to do, but this contributed much to how heavy the resources are being used. But generally speaking, apart from the training and augmentation, the model is pretty small. It's like 3 conv layers and 3 gated recurrent layers. It's working only on like really small images. So I think it's like for an inference point of view, I think it's really small and fast. I don't have an actual number right now. That's forgive me for that, but it should be like resource friendly in inference time at least.
Okay. Yeah.
Yeah.
So someone says, so you end up feeding one data point per each field. That's the 3,600 data points only, or one data point per each pixel. Uh, Try reading your services if you understand it. Uh,
End up feeding
so that you end up feeding one data point per each field. I'm not sure.
yeah, yeah. So each yeah, yeah, yeah. All the fields fit in the 32 by 32. I guess only I I didn't like uh, quite make like an exhaustive search, but like there is a field with more than 300 pixels. This might get out of the 32 by 32 if it is not like in a rectangle shape. But this didn't quite made any problems because like most of the fields are actually less than 50 pixels. So it's definitely inside the 32 by 32. So on each of the crop fields is only represented once by 32 by 32 batch.
Yeah, I think I wanted to clarify. I wanted to make you clarify this so that it doesn't look like for each crop field you cut out 32 by 32 so multiple times, but it just means that you pick it once and most of the crop fields will all be covered. Like everything
Yeah,
will be covered at once. And
yeah, yeah.
if everything is not covered, at least it will cover the most part of it. So you pick each crop field once and feed it to your neural network. Is that right?
Yes, yes, exactly. So I take for each field, I calculate only a single center for each pixel,
Yeah. So
for all the pixels, and around this center I take my patch only once.
yeah, so it's around the center because that's
Yes.
very important. So it's around the center that you take the 32 by 32 around. So yeah,
Yeah, yeah,
and
exactly.
one. Cool. Okay. I don't know if there are any other questions. Not so sure. Okay. How did you constitute the input as a 4D tensor?
Um, so I used the library I used in training all this stuff was PyTorch, and it's quite easy. So like by concatenation of all time steps and all spectral bands, you end up with a 4D NumPy matrix at first, and you transform it to like a PyTorch tensor afterwards. Uh, so it's really straightforward in PyTorch, thankfully.
Coming, you combine the channels plus the time steps and the.
Sorry, I didn't hear you well in the first place.
You said you combine the time steps, the channels, and what again?
Yeah,
Only the.
at the first I have like 13 different images,
Mhm.
and each image has a 13 spectral band. So I construct like a large 4D matrix for all of this stuff and keep concatenating all of them. So it's like a nested loop on the time steps and all the spectral bands.
Uh, okay. That how large was the entire data set after all the augmentations, rotations, flips, etc. you applied?
So I'm the way I apply the augmentation is I apply it on the fly. So I didn't actually generate them and save them on the disk, for example, to make everything fast. So like each augmentation is applied with a probability of 50%. So if in 50%, I do the flipping. In 50% probability, I do the rotation and etc.
Mm. Uh, I don't think there's any further question. So yeah, not sure there are other questions again. So I think that will be all for now. Thank you very much, Karim, for your time.
Thank you, John, for
Um,
having me.
yeah. This has been so helpful. I've personally learned a lot from it, and I think it has also been helpful to the other participants. So, like I said, we are recording this, and it will be uploaded to our YouTube channel, and the links to the repo and the slides will all be made available. And if there are your LinkedIn, Twitter handles, and everything is available, so people will be able to contact you personally for assistance and all that.
Yeah,
Also,
yeah,
thanks to Zindi once again for the platform and for giving you to us. Yeah, I mean, for giving us the awareness to present. I mean, that's, yeah, yeah. I mean,
Yeah,
that's too big.
it's
It's
a
big
great
for
opportunity to talk to the community. I
yeah,
It's like a short time,
because
but
yeah, I personally like competitions, and I would up my skills, and it will help me perform better on future competitions. So, and I think that it will help the other people as well. Yeah,
thank you.
this is why yeah. So I'm much grateful to Zindi, and so thank you very much for your time.
Thank you,
Yeah.
John, and thanks to everyone for listening. And I hope you mentioned anything useful to you in the future. And I hope we can meet again on the
Some other
on
time.
that
Yeah.
time. Yeah.
So if we see your name pop up in another competition, we'll be sure to contact you, and you.
I hope so. Yeah. I would be happy to do it again.
And to everyone who tuned in to watch us, that we very much appreciate that. Keep on tuning in to learn, share, ask questions, and let us all together learn a lot. I know that we are going to be collaborating a lot in the future. So let's keep doing this, keep supporting us, and let's keep interacting and helping ourselves. Thank you very much. My name remains John Baglico, the team lead for AI Ghana and data scientist at Superfluid Labs. And